Chemical bonding and Lewis structures. So when you have a compound, your atoms in a compound are held together by a specific type of bond. Depending on the type of bond that you have, you're going to have a specific type of compound. And we use Lewis structures to represent how the atoms are bonded together, forming that specific compound. Lewis structure is just a model, so it's a drawing that I'm going to show you how to get, and they also call electron dot structures because we actually use dots to represent electrons. Now, the two types of compounds that I was talking about is the ionic and the covalent compounds. In covalent compounds, they're also referred as molecular compounds. Ionic compounds are the type of compounds that is going to have ionic bonds. When you have ionic bonds, you have an ionic bond because opposite charges are attracting each other. So for you to have ionic bonds, they have to be transfer of electrons. Electrons, they need to move from one place to another, so you can form positive and negative ions, and then your ionic bond is going to form between the attraction of your opposite charges. In general, when you have ionic compounds, you're going to have a metal. And the metals, they form cations or ions with a positive charge because they tend to lose electrons. And your metal can be forming an ionic bond with a non-metal or with a negative polyatomic ion. But everything else that I'm going to be doing today, it's about covalent compounds. So in your covalent compounds, what is actually happening is that there's sharing of electrons. Instead of just transferring the electrons, the elements, they're going to share the electrons, forming a chemical bond. And when you have sharing of electrons, what you have is a covalent bond, and you will have a covalent compound. So all of the elements in the periodic table, all of them, are going to lose, gain, or share electrons if you have covalent compounds to have the same number of valence electrons as the noble gases. So your noble gases here in group 8, they have 8 valence electrons. And when you have, for example, nitrogen in group 5, it contains 5 valence electrons, but the ion of nitrogen with a charge of -3 will have now 8 valence electrons. So your ions, they're losing or gaining electrons to have the same number of electrons as the noble gases, 8. And then when you have atoms in covalent compounds, they will be sharing the electrons to have 8 valence electrons. And that is what I have right here. That's an octet. So every element in the periodic table will form compounds, ionic or covalent, to have an octet, which means that they want to have 8 electrons in that highest energy level. And then the electronegativity, which is a property that we can predict using the periodic table, similar to what we do with the atomic size. It's something that I'm going to refer later. You will see it like a little bit when we're drawing the Lewis structure, but we use this actually to determine which type of bond you have. So it's just a property that describes how much an element likes electrons. So when you're sharing the electrons, specifically when the electrons are being shared, your electrons can be equally shared between two atoms that have a equal or similar electronegativity, or your electrons are going to be unequally shared if you have something in that bond that has a high value of electronegativity. When something is very electronegative, what that means is that it likes to pull the electrons towards itself. So when you have your electrons in a chemical bond, if out of your two atoms forming the bond, one is very electronegative, the electrons in that chemical bond are going to be closer to that atom that has a higher electronegative value. And we can use the periodic table to predict like electronegativity trends, not an actual number, but just in comparison to other elements. So electronegativity is increasing as you move to the right and as you move up in the periodic table. And I have there fluorine, because whenever you get to see the numerical values for electronegativity, you will see that the numerical value for fluorine is the highest out of all the elements in the periodic table. So we have the octet rule, which is telling us that everything in the periodic table wants to have an octet or 8 valence electrons, or to have 8 electrons in that highest energy level. But there's always exceptions to every rule, and we have elements that they can actually have more than 8 electrons around. So those elements, they can get an octet with 8 electrons, but they have enough orbitals to accommodate additional electrons. So you can have elements with 10 or 12 electrons around, and that's perfectly fine as long as they are part of these exceptions right here. So when you are in the third period in the periodic table, which is when you have sodium all the way to argon, that's your period 3 right there. When you're looking at elements in that period or any period higher than the third one, going down in the periodic table, your elements, they can actually accommodate more than 8 electrons because they do have the orbitals. So they're going to have orbitals available where they can have additional electrons above 8. And then the second group of exceptions are elements that are going to have a complete octet with less than 8 electrons. So hydrogen, which is the first element in the periodic table, you have one electron for hydrogen. And for hydrogen, there's just one orbital, the s orbital in the first energy level. And you know that in each orbital, you can have a maximum of 2 electrons. So for hydrogen, there's no orbitals where to put more electrons than just 2. And then we have 2 more exceptions: beryllium, which is going to have a complete octet with 4 electrons, and then we have boron, which is going to have a complete octet with 6 electrons. So elements in the periodic table in the third period or any period higher than the third one, they can have an octet with 8 electrons, but they can also accommodate more than 8. And then hydrogen, beryllium, and boron, they will be happy with less than 8 electrons, specifically hydrogen with 2, beryllium with 4, and then boron with 6. So to draw Lewis structures, you can find many different ways of doing this. These are just steps that are suggested for you to follow, and the more you practice how to draw the Lewis structures, the easier it will get. So I have here for the first step, like your compounds, they're going to form your chemical bonds by losing or adding electrons to the valence shell, or by sharing electrons, but those electrons that are shared are the valence electrons also. So all of the chemical bonds that you're getting in a molecule or in a compound are due to the transfer of electrons, and those electrons are the valence electrons, or to the sharing of valence electrons. So the first thing that we're going to be doing is counting a total number of valence electrons for the specific molecule that you're trying to draw the Lewis structure. So you know that you can find the number of valence electrons from the periodic table for the elements in the periodic table. So if you have them in a compound, you just need to add all of those valence electrons together. That is going to give you a total number of valence electrons that are used now to form all of the chemical bonds in your actual molecule. So I'm going to start with the first one here. I have 4 examples, and we're going to do all 4 of them, because with these 4 we can actually go over what you have to do when you have an anion or a cation. So for CH4, you have carbon, and carbon is right here in group 4. So every element in group 4 is going to have 4 valence electrons. And then you have hydrogen, and hydrogen is in group 1, which means that it has 1 valence electron. So I'm going to put 1. And you know you have 4 hydrogens, which means that each hydrogen is giving one valence electrons for the formation of chemical bonds in this specific compound here. So I'm going to put times 4 right there. So now we need to add all of them together. So you have 1 times 4, which is 4, plus 4, that will give you a total of 8 electrons. So this is how you calculate the total number of electrons for a neutral molecule, because there's no charge in CH4. Then we have NH4 plus 1 here, and for NH4 plus 1, your molecule here has an overall charge. So now you have an overall charge which is a positive, and whenever you have a positive charge, you need to subtract as many electrons as the charge is telling you. So let's start with nitrogen. Nitrogen, it's in group 5 in the periodic table, so that's 5 electrons. And then you have hydrogen, and hydrogen is in group 1, that's 1 electron. But you have 4 hydrogens, so we need times 4. So that's going to give you a total of 5 plus 4, 9 electrons. And now we need to subtract 1, because your molecule here is actually a polyatomic ion, and you have a charge of positive 1. And whenever you have a charge that it's a positive, you need to subtract as many electrons as the number that you have for that charge. So that's 1 electron. That's going to give you a total of 8 electrons for NH4 plus 1. For NH3, nitrogen, again, it's in group 5, that's 5 valence electrons. Hydrogen, it's in group 1, that's 1 times 3. When you add all of them together, that's 8 electrons that we're going to use to form all the chemical bonds. Those electrons are going to be shared between your nitrogens and your hydrogens, forming the Lewis structure. And then we have PF6 right here, and phosphorus is right under nitrogen in the periodic table. And then you have F, which is in group 7 in the periodic table. So for P we have 5 electrons, for F we have 7 electrons, and we have 6 F's in that molecule right there. So that will be times 6. And this is also a polyatomic ion. You have covalent compounds between P and F, but you do have an overall charge. So that overall charge, or now it's a negative number, which means that that's an anion, and you need to add as many electrons as the number of the charge that you have. That right there is your 47 electrons, but you have a charge of -1, so that's adding 1. And that's going to give you a total of 48 electrons. So this is the first thing that we have to do, okay? Counting how many electrons you have to form all of the chemical bonds in your covalent compound. Now, sometimes you will have to determine which one is the atom that you're going to put in the middle of your molecule to connect everything to it. And that's what you're doing. You're trying to show like how all of the atoms in your compound are connected to each other. So in some cases we need to use this here, where the least electronegative atom will be the central one, and I will give you an example where you have to actually use this. Whenever you have hydrogen, hydrogen can never be the central atom because hydrogen can have only 2 electrons around. It's one of the exceptions. So hydrogen, it's usually on the outside, or it's classified as a terminal atom and not as a central atom. And then in all of these examples, these are easy to identify which element is going to be the central one, because you have 1 carbon, so that should be the central one, 1 nitrogen, that should be the central, 1 nitrogen here, the central again, and you have 1 P and 6 Fs, so P should be the central one in this case. So that's all for our step 1. It's just counting how many valence electrons we have in total. And now we're going to put the central atom for CH4, that's the. And then we're going to use our number of electrons to form bonds between the central and every other atom in the compound. So let me write down here how many electrons we calculated. For that one was 8, for this one was 8 also, for this one was 8, and for this one we have much more than 8, 48. So with our total number of electrons that we calculated already, we're going to form chemical bonds between the central and every single atom in that molecule. So what I always do is to bond my central with my hydrogens. I have 4 hydrogens, so I'm going to put 1 line for each hydrogen. And now I'm going to put my hydrogens. So I have my central atom carbon forming a chemical bond with each one of the hydrogens that I have in my compound CH4. So that's what you need to do for that step right there. Now here we have nitrogen and 4 hydrogens. So since you have 4 hydrogens, you need 4 lines around your nitrogen, and each line is going to be connected to one of the hydrogens. NH3, now you have only 3 lines because you have 3 hydrogens. And then PF6, you have 6 lines because you have 6 Fs. 1 line per every single atom that you have to connect to your central. So the idea or the goal is to form chemical bonds between all of the elements that you have in your compound, but you need to follow the octet rule. Everything is sharing electrons, forming those chemical bonds to share electrons, to have 8 valence electrons or 8 electrons around, with the exception of those atoms that are going to have an octet with less than 8, like hydrogen. So each hydrogen here in your CH4, it's forming, each one is forming 1 bond with the central atom. So for example, if you're looking at, let me find it. If you're looking at this hydrogen right here, that hydrogen is sharing that line with the carbon. That line right there represents 2 electrons. So every time that we want to put 2 electrons between 2 atoms in a compound, we're going to use a line, and that's 2 electrons, and that line is known as a single bond, which is what I have right here. So that line that you have right there in pink represents 2 electrons that are being shared between your carbon and that specific hydrogen. Hydrogen has a complete octet with 2 electrons. You have it in your exceptions. So hydrogen, it's happy with 2 electrons because for hydrogen 2 electrons means a complete octet. Each hydrogen in that CH4 compound, it has exactly the same thing, sharing 2 electrons with the carbon, so each hydrogen has a complete octet. So that hydrogen is also happy. That hydrogen happy with 2 electrons and happy with 2. So if each line represents 2 electrons that are being shared between the carbon and each specific hydrogen, around carbon you have 8 electrons in total, 2 electrons in every single line. So 2 here, that's 2, 4 in this one, plus 2 here, that's a total of 6, plus 2 in this one, that's a total of 8. So for carbon, you have 8 electrons around, and carbon has a complete octet, which means that that molecule right there, we have a complete octet for the hydrogens with just 2 electrons in each one, and a complete octet in carbon with 8 electrons around. So that's the correct Lewis structure for that molecule. You're using your 8 electrons right there. All of them, you have used them. And you have a complete octet in everything. The terminal atoms, which are your hydrogens, and the central one. Then we move to the second one here, where you have a total of 8 electrons, and you're using 2 electrons in each line to connect your nitrogen with your 4 hydrogens. And if you check, you're using all 8 electrons. You have a complete octet for each hydrogen, because for hydrogen you just need 2. And then around nitrogen, you have 8 electrons. Nitrogen is sharing 2 electrons with each hydrogen in that compound, and you have a total of 4 hydrogens, a total of 4 bonds around nitrogen, so each bond is 2 electrons. That's a total of 8 electrons. So for NH4, you have a complete octet in your terminal atoms, in your central atom, and you're using a total of 8 electrons, so that one is the Lewis structure with a minor modification, because whenever we have a charge, we have to put our structure in brackets and including the charge that we have. And now we're going to do this too, where we actually have to use step number 3. So we counted the total number of electrons, we put the central atom here, and we have the central atom connected to each one of the hydrogens in your molecule. Now we need to check, we have 3 hydrogens and we're using 2, 4, 6 electrons around the nitrogen. We have a total number of electrons that is equal to 8. Out of the 8, we're using 6 to connect the hydrogens with the central atom nitrogen. Your hydrogens, all of them, all 3 of the hydrogens here, have a complete octet, but not the nitrogen. For your nitrogen, you need to have 8 electrons around, and right now there are only 6, which means that the nitrogen is missing 2 electrons to have a complete octet. Now in your step number 3 here, this is telling you that if you have electrons that you're not you're not using, right? After forming the bonds between the central and all of your atoms, you need to use those electrons to complete the octet in your terminal atoms first. But your terminal atoms here for NH3, it's hydrogen, and hydrogen has a complete octet with just 2 electrons, which means that you don't have to use your 2 remaining electrons here to complete the octet in any of your hydrogens, but you need to use those 2 electrons to complete the octet to your nitrogen, because you don't have enough things bonded to your nitrogen to have a complete octet. So whenever that happens, we can add those electrons as a single pair of electron or non-bonding pair of electron. And the electrons are always in pairs. We're using a line, and that line represents 2 electrons. So when we're using lone pairs of electrons, we're actually writing them as a pair of electrons like that. Lone pairs of electrons are also known as non-bonding pairs. And we can complete octets forming chemical bonds or sharing electrons between 2 atoms, or we can actually use electrons as lone pairs of electrons to complete the octet of an atom in a molecule or in a compound. Now, for PF6, you have P as the central atom, and you draw 6 lines around because you have 6 Fs. Okay. So far, that's what you know. And now we need to complete the octet in your terminal atoms here, because your terminal atom, for the first time out of my 4 examples, this is the first one where the terminal atom is different from hydrogen. If your terminal atom is hydrogen, once you form your bond between the terminal and the central atom, your hydrogen has the complete octet. But now you have something that is different from hydrogen, which means that your F, it needs to have an octet also. So we complete the octet doing this right here, which is just adding pairs of electrons around that atom. So I'm going to start with this F here, that one right there. And that F is sharing 2 electrons with the central P, which means that to get to 8, that F it's missing 6 electrons, because remember, you want an octet and you need an octet with 8 electrons. So you have 2 in the single bond, and now you need to put 3 pairs of electrons around F, and your 3 pairs of electrons, it's 6 electrons plus those 2 right there in your bond. That will be a total of 8. And for each F, you have exactly the same. Each one is missing 6 electrons to go from 2 all the way to 8. So in this case, you have your central atom B surrounded by 6, and you should be noticing something. And you have your F's that you completed the octet using lone pairs of electrons. And you need to check that everything has an octet and that you're using as many electrons as the amount that you calculated. No more or less. It's exactly that amount. So you can count and you will see that you're using all 48 electrons so far. And now this is an ion, and that should be in brackets with the charge -1. I hope you noticed this, but around P you have 2, 4, 6, 8, 10, 12 electrons. You have 12 electrons around P because you have 6 lines connecting your 6 terminal atoms, right? And in each line, what you have is 2 electrons. So that's a total of 12 electrons right there. And you're looking to have an octet in everything. but for P you have more than 8. And that is perfectly fine whenever you have an element that is in the third period or any period higher than the third one. Okay? So P is in the third period. Phosphorus can have an octet with 8 electrons, or it can actually have expanded octet. It can have more than 8. It can have 10 or 12. So if you have 12 electrons around P, that is perfectly fine because it's in the third period. Something like this cannot happen with the nitrogen or with the carbon. Nitrogen and carbon, both of them are in the second period right here. So for nitrogen and carbon, you need to have an octet with 8 electrons. That something like this cannot happen with the elements that you have in this second period. It can happen with something in the third or anything higher than that, but not with elements like nitrogen or carbon. And now I have here an example where we actually have to use the electronegativity to determine which element is the central one. So you have a node that tells you that the central one or the central atom should be the one with the least or the least electronegative one. Hydrogen is never a central atom because it can have only two electrons around, or one single bond, that's it. So between carbon and nitrogen, you need to check the periodic table, and the electronegativity trend, it's telling you that the electronegativity value is increasing as you move to the right side and as you move up. Which means that nitrogen is here, carbon is here, and if the electronegativity is moving in this direction, nitrogen is going to have a higher value of electronegativity than carbon, which means that the central atom is the least electronegative out of these two, and that's going to be carbon. So I'm going to put carbon as my central. And we need to count how many electrons we have to form all bonds in this molecule. So for hydrogen, that's 1 electron, carbon is in group 4, that's 4, and then nitrogen is in group 5, that's 5. And that will be a total of 10 electrons. So we have a total of 10 electrons to form the chemical bonds between the carbon, the hydrogen, and the nitrogen, and to have a complete octet for everything. So a single line connecting the central and your terminal atoms, so that's carbon connected to hydrogen, carbon connected to nitrogen. Okay. Now, in this case, your hydrogen has a complete octet, just with that line, complete octet. Carbon and nitrogen, you need 8 electrons, 8. Out of the 10, you're already using 2 and 2. You're already using 4 electrons out of the 10, which means that you have 6 electrons left. 6 electrons to complete the octet to your carbon and your nitrogen, to both of them. And those 6 electrons are not going to be enough. They're not going to be enough. I'm going to use your electrons following your rules right here, this step, not rule. Step number 3, you form your bonds, and then you move to complete the octet to your terminal atom. So I'm going to complete the octet in the nitrogen. So nitrogen is missing 6 electrons to complete 8. So that's 2, 4, 6. So I'm using 2, 4, 6, 8, 10 electrons. I'm using 10 electrons, which is what we have, a total of 10. Nitrogen is happy, hydrogen is happy, but carbon is not happy, because for carbon you have 2, 4 electrons around, and you need to have a total of 8 to have a complete octet. So carbon is not happy. Whenever something like this happens, you need to share more than one pair of electrons around the carbon. We can have a single bond when you're sharing one pair of electrons, like in all of the ones that we did before. Single bond sharing 2 electrons between your atoms, 2 electrons between nitrogen and hydrogen, 2 electrons right there between P and F. But we can share 4 electrons forming a double bond. We can share 6 electrons forming a triple bond. And you are going to use multiple bonds, double or triple, whenever you don't have enough electrons to complete the octet to everything in your compound. So I'm going to put not between hydrogen and carbon because hydrogen is good. Instead of having 3 lone pairs of electrons here around the nitrogen, I'm going to share 2 pairs of electrons between the carbon and the nitrogen. It's like I'm moving this one between carbon and nitrogen, and that will give you something like this. Something like this: 2, 4, 6, 8, 10 electrons, a total of 10. Nitrogen, it's happy, 2, 4, 6, 8. Hydrogen, it's happy because you have your 2 electrons there. But carbon is still not happy because now you have only 6 electrons around carbon. It's improving. We went from two bonds here with 4 electrons to 3 bonds around carbon, that's 6 electrons, but it's still not 8. So if I share another pair of electrons between carbon and nitrogen, right now everyone is going to be happy because every single atom in that structure right there has an octet, and you're using a total of 10 electrons, which is what you have available to draw your Lewis structure. So hydrogen, it's happy with 2. Your carbon, you have 2 electrons in each line, 2, and then you have 3 lines here with 2 electrons in each one, that's 6. So this 6 plus 2, that's 8. For your nitrogen, nitrogen is sharing those 6 electrons with the carbon, so they count towards your carbon and also towards the nitrogen. So you have 6 plus these 2 electrons that are forming a lone pair of electrons, that's a total of 8. So everything has a complete octet, and you're using the total number of electrons that you calculated in the beginning. So those 2 things you need to check before you finish your Lewis structure. When you have your drawing, you're going to check if you have a complete octet for everything. You might have more than 8. You need to check if you have more than 8 that element is in the 3rd period or anything higher than the 3rd period. You have exceptions where you're going to have an octet with less than 8, like for hydrogen, for example. And you need to check that you're forming all of your chemical bonds and all of your octets with the total number of electrons that you calculated. No more, no less.